Welcome to the Unit 11 take-home test for acids and bases. Okay, let's take a look at this first little section. Okay, we're comparing and contrasting acids and bases. So acids tend to taste sour. Acids are electrolytes. They react with metals to produce hydrogen gas. Okay, the ion that acids release is right here as the Arrhenius definition as well, but that's the hydrogen ion, which are also known as protons. pH range for acids would be 0 to 7. Okay, acids will turn litmus paper red or keep red litmus paper red. Okay, when it comes to properties of bases, I'm going to offer, if y'all are getting this down, 2 points of extra credits. We said big, blue, bitter, bases. Okay, big, blue, bitter, base. So it's a big pH, 7 to 14, turns litmus paper blue or keeps litmus paper blue, tastes bitter, that's how you know it's basic. Alright, so use that information to help you fill in this one. As we're looking down here, the Arrhenius definition is A, the classroom definition that we have A always used in class, saying that acids start with H and release H+, bases always end in OH and release OH-. The Bronsted-Lowry base is more concerned with protons. Okay, you can even kind of say he's the proton guy. There's the P for proton hiding in his name. So for a Bronsted-Lowry acid, we're talking about a proton donor, and for bases, proton acceptor. Okay, so we'll give away an H+ or we'll take away an H+. Okay, something to memorize, maybe make flashcards if you're having a hard time understanding. Okay, I want you all to do these ones on your own. I should have highlighted those ones in blue. And I want you to do these ones on your own. But let's look at 6, 7, and 8. Okay, which of the following would not form electrolytes? So I had a student, shout out to Megan, say that ABs are electric. Okay, acid, base, salts are always electric. So this starting with an H is an acid, so it is an electrolyte. NaCl, that's a metal and a nonmetal, so that's an ionic salt. That is an electrolyte. Ending in an OH means it's a base, and that is an electrolyte. But PO4, those are both nonmetals, so this would be a covalent compound. And covalents do not conduct electricity, so that one is not an electrolyte solution. Neutralization is always a reaction between an acid and a base to produce water and some kind of ionic salt. Okay. So neutralization reactions are also double replacement reactions, but it's always an acid plus a base. So this plus this, this plus this would be an example of a neutralization reaction. Strong base, strong versus weak. Okay, strong means 100% of the time, complete dissociation. That means you're going to have a lot of base ion because it's a strong base, making it very good at conducting electricity. If there are a lot of electrolytes, then you're really good at conducting electricity. Alright, so let's look at number 11. Solution A, and if we're looking at the pH scale 0 to 7 to 14, solution A has a pH of 2. So we're right about there. When you mix in unknown solution B, the new pH is over here. It's a pH of 9. So solution B must have been blank. Okay, if I'm going from 2 to 9, I'm getting more basic. The only way to get more basic is by adding base, and the base ion is hydroxide, the OH ion, like that. Okay, that's page 1. A lot of vocab, which is good. Once you know it, you know it. Let's look at page 2. Page 2 has a fair amount of formula writing and naming. So the stuff that's already there, you can see the stuff that's in blue is stuff for you to do on your own. But let's take a look at what we have highlighted in yellow. So for the things highlighted in yellow, we're looking more like this for acids. Okay, Remember, if it begins with an H, it's an acid. and then it's either a binary or an oxyacid. Only binary acids start with hydro. Oxyacids do not have hydro as a prefix. And we say bites, artilish us, and I ate too much, so I feel icky now. Okay. So if we are looking here, we'll leave in this one D, H3P. I've got two capital letters, so two elements means binary, so I'm going to call it hydro something ic acid, and phosphorus will make phosphoric acid. So hydro phosphoric acid. Okay, hydrophosphoric acid. For this one, I cannot call this one hydro, HC2H3O2. Because it has oxygen in it, or it has three or more capital letters, that means I do not use hydro as a prefix. I have to find the polyatomic ion, which is C2H3O2. And on our list for C2H3O2, that's acetate. Okay, so it's hydrogen bonded onto acetate. I ate too much, I feel icky now, so I'd call it acetic acid. Not hydroacetic acid. Technically acetic, but it's easier to pronounce it acetic, I get that. Alright, sulfurous acid, sulfuric acid, and hydrosulfuric acid. So the big difference is kind of these two, sulfuric acid and sulfuric acid. Just the hydro is the difference. So sulfurous acid, okay, bites, artilish us, used to be sulfite, I-T-E. Sulfuric acid, I ate too much, I feel icky now, used to be sulfate. And a hydro, if you see hydro in the beginning, it means it's just hydrogen bonded onto sulfur. So this is going to be hydrogen bonded on to sulfite for that first one, SO3, making a -2 charge. This one is hydrogen, because it ends in acid, bonding on to sulfate, which is SO4, making a 2 charge. And this one is hydrogen, because it's an acid, bonding on to hydrosulfuric is just sulfur, which also makes a 2 charge. And the hydrogens make a 1. So we crisscross those charges. The 2 comes here, the 2 comes here. So this one is H2SO3. This one's H2SO4. And this one's just H2S. And for these ones, it can just be H2SO3 without parentheses. H2SO4. Okay. Either way is acceptable. So again, if you're struggling on that, go back and watch that video tutorial from the day 1 homework that talks more about naming acids and writing formulas for acids, because that's a big part of this test. If you have an equal concentration of hydrogen and hydroxide ions, then they're going to cancel out. The positive and the negative are going to bond onto each other, and you're going to get H stuck to OH, which is just H2O. And I'll tell you what, if you write that down, you get +2 extra, whoops, that's K, extra credit. Okay, the H plus and OH minus is just water. So if it's water, then your pH is going to be neutral, pH of 7. They cancel out. That's called neutralization. If you have just a little bit less acid and just a little bit more base, then you're going to be slightly basic. So this one's slightly basic. pH of 6 is slightly acidic. This one's super acidic, and this one's neutral. So that makes my answer just a little bit more base than acid. If there are significantly more acid ions compared to base ions, then I'm not going to be slightly basic. I'm not going to be slightly acidic. I'm going to be significantly acidic and not neutral. Okay. If we're looking down here, milk has a pH of 6.6. That makes it acidic. Not very acidic, but a little bit acidic. And litmus paper is always red when it's an acid. So we said on the first page, big, blue, bitter, base. Blue litmus paper stays blue if it's basic. So for apples, 3.2, that one's much more acidic, but still acidic, which means, again, that the litmus paper will turn red. 21 is talking about these pHs. Which material above has the highest concentration of H plus ions? The most H plus means the most acidic. Which one has the highest concentration of OH ions? That's the most basic. So look at those pHs to answer saliva, milk, seawater, or apples. Go ahead and answer those ones on your own. Page 3. All right. Here we go. If a solution is becoming more acidic, it is lowering or raising its pH and increasing the concentration of the blank ion. So, again, we said on the pH scale we've got 0, 7, and 14. So right here is neutral and safe. So if we're becoming more acidic, that means we're getting further and further away from neutral in that direction, which means my pH is getting smaller. Because it's big blue bitter base. That's where we're basic, is up here. And if we're getting more acidic, that means we're getting more of the acid ion, the H plus ion. Okay, right here I'm going to give you all 2 points of extra credit if you were writing this down. Okay, acid plus base results in water plus salt, and that is a neutralization reaction. And I don't know if I can spell that. UTR. Okay, I got lost halfway through, so about neutralization, kind of, sort of. Okay, it's also a double replacement reaction, which we learned about back in Unit 4, I think, when we learned about types of reactions. Okay, so it says use the acid's hydrogen and the base's hydroxide to make water. What's left will make the salts. Use the box provided to write the salt's formula, and remember to look at the charges. Then name each compound and circle the salt. So I did that one already for you on 23. You can check your work. If we're looking at 24, acetic acid, we already wrote that formula for you. And I'm going to add back in those parentheses just so you can see them. Aluminum hydroxide, we already wrote that formula for you. So an acid plus a base is always going to make water and some kind of salt. So the water, I'm going to get this H bonded on to this OH. Okay. Hydrogen was in front, so it stayed in front. Aluminum was in front, so it's going to stay in front. And now aluminum, instead of bonding onto hydroxide, is going to bond onto acetate. C2H3O2. Okay, but we're not done. That's just step 1 of our formula writing, symbols. Then we need to do charges. So aluminum is one of the 3 in 3A that always makes a +3 charge. Acetate on my polyatomic ion list makes a -1 charge. Then we crisscross. The 1 comes here, and the 3 goes in the back. Okay, and the 1's invisible. So Al C2H3O2 3 is going to be that formula. And we're going to call this aluminum acetate. Okay, so over here it was acidic because it was in an acid. But here it just says acetate because this is my salt. Just a normal, regular ionic compound, ionic salt. Yeah, it's not a balanced equation, but that's all right. We're not worried about balancing on this page. All right, so I gave you some of those other answers. Take a look at them. Down here for number 27, if a solution contains 1 times 10 to the -8th molar of hydrogen ions, what's the pH? So we always grab our exponent and make it positive. pH of 8. Okay, and being bigger than 7 means that we are basic. Okay, so this would be a big blue bitter base. Okay, can you check any of those other answers? Go ahead and push pause. Otherwise, let's look at page 4. Okay, so in the true-false sections, we wanted you to write true or false and then correct the false statements by changing word or words. So I've done that. You can compare your answers to what I got. Down here for the matching stuff, I want you to do the blue ones, but let's look at these yellow ones. So red litmus paper will stay red, blue litmus paper will turn red, and red litmus paper turns blue. So we said again, big blue bitter base. So if it turns blue or stays blue, this one's going to be basic. For this one, we're on red litmus paper, and if it stays red, then we're acidic. Okay, and blue litmus paper turning red is also acidic. Okay, so we're looking here. Indicates the substance must be basic. That one's going to be 44, D. Indicates the substance must be acidic. Turning red means you have to be acidic, so that one's going to be our E. F indicates that the substance could be acidic or neutral. So if red litmus paper stays red, it might be acidic, but it also could be neutral. Okay, so we're going to say F for that one. Alright, looking down here at 48. Circle a solution that's the most basic. That's the biggest pH, is the most basic. So pH of 12. Solution has a hydrogen ion concentration of 1 times 10 to the negative 11th. So that means the pH is going to be positive 11. What is the pH of a 1 times 10 to the negative 6th molar concentration of a hydrogen ion? So to the negative 6th means positive 6 pH. Okay. And being less than 7 means that this is an acid. And how did I know? Because low pH equals acidic. Right? Page 5. Okay, I'm going to offer some extra credit here as well. Alright, if you're writing down +2 extra credit, 0 to 7 to 14, I want you to write neutral above where it says 7. Bigger than 7, so everything over here would be basic. Okay, big on the pH scale is basic. Excuse me. And everything lower than 7 on the pH scale is acidic. So that should help you answer these ones right here. Really, a lot of questions come from knowing this about the pH scale. For some safety stuff, we gave you some tips over here. Okay? What are 2 things you should do if you spill an acid on your skin or in your eyes? The first thing you do is tell your teacher. Or have someone tell the teacher. Okay, but really what the teacher's going to have you do is flush it out with water. Flush with water. Okay, so you're going to need to use the eye wash station if it's in your eyes, a sink or the shower depending on where you get it on your skin. If it gets on the clothes, then the clothes need to come off. Okay, otherwise that's what we do with acid spills, is we need to dilute it. Okay. Neutralization reaction, again, is going to be acid plus base makes salt and water. Okay, base plus acid is salt and water. That works as well. So for balancing, it's always going to be a good idea to add your parentheses back in on the polyatomic ions. So HClO4, ClO4 is a polyatomic ion. That one's already in parentheses, that one is. And then I crossed out water, I made it HOH because it's still H2O. It's just going to make it easier to balance this way. So I'm going to divide my reaction in half and write down what I have. I have hydrogen, I have ClO4, I have magnesium, and I have hydroxide. Okay, those 4 things I'm going to balance. And I'm going to copy it down in the same order over here. ClO4, magnesium, and hydroxide. Okay. Then I count how many I have to start with. I have 1 of these and 1 of these. I have 1 of these and 2 of those to start with. Hydrogen, I have 1 of these. I've got 2 ClO4s, 1 magnesium, and 1 hydroxide. So we start from the top and work our way down. To start with, my hydrogens are already balanced. My ClO4s are not. So I go to the smaller side, right here. And in order to make this one match, I have to multiply by 2. So I'm going to put the 2 there. But by putting the 2 in front of the HClO4, that doubles my ClO4s and my hydrogens. So even though I didn't want to, I did, which means my hydrogens are not balanced anymore. So I'm going to come back up. I've got 2 hydrogens on my reactant side and 1 on my product side. So the smaller side here I need to multiply by 2, which means I'm going to put the 2 there. That gives me 2 hydrogen, but it also gives me 2 hydroxides. Okay. So my hydrogens are balanced at 2, my ClO4s are balanced at 2, my magnesiums are balanced at 1, and my hydroxides are balanced at 2, which means everything else stays the same. I just put 1s in the blanks. So my coefficients are 2 to 1 to 1 to 2, like that for balancing. Alright, same thing down here. I'm going to add back in my parentheses. Cr2O7 is dichromate, which makes this dichromic acid. And this is beryllium dichromate as my salt. And I already changed my HOH there. So I'm going to cut this in half, write down beryllium, hydroxide, hydrogen, and dichromate on both sides. Okay, pause to catch up if you're working along with me. Oopsie, Cr2. Okay, if we count what we have, I've got one of these and two of those, 2 hydrogens and 1 dichromate, 1 beryllium, 1 dichromate, 1 hydrogen, and 1 hydroxide, like that. Okay, so berylliums are balanced, hydroxides are not, which means I need to double my product side. I'm putting a 2 there. That doubles hydroxide, but it also doubles my hydrogen. Okay, so berylliums are balanced, hydroxide's balanced, the hydrogen's balanced, and now dichromate's balanced. So that was all I needed to do on that one. So it's 1 to 1 to 1 to 2. 1 to 1 to 1 to 2. That was not so bad. But let's come back here. It says to circle the salts. That's my ionic thing. So the metal bonded onto the nonmetal. That's this guy. Those are all 3 my salts. To box in the acids, so what starts with the H's. So this would be ClO4. Is that chlorate? Perchlorate. So this would be perchloric acid. That's a base. Right here, that'd be dichromic acid. And this one would be hydrofluoric acid. And to put a star by the base, so my OHs. So right here, magnesium hydroxide, beryllium hydroxide, aluminum hydroxide. So I see that all of these are neutralization reactions. Okay, looking at the last page, we've got some fill in the blanks here. Okay, looking first at our conductivity tester pictures. So they said the first one, whatever solution this is, it makes the light bulb bright. Whatever solution this is, the light bulb is off. So here's our word bank, I guess. On the illustration below, the light bulb on the left is very bright. The strong current of electrons is possible because of the high concentration of ions in the solution. High concentration of ions are produced by the complete blank of strong acids and strong bases. Okay, that's going to be dissociation. Okay, so that would be complete, like we said, dissociation. Now remember we said dissociating is dissolving with a charge, so making ions. That means ions are not connected to each other anymore, but have dissociated into the water. On the other hand, blank acids and bases do not dissociate completely. Okay, so that's going to be weak. Acids and bases do not dissociate completely, so they would produce only a weak current of charges, resulting in a dim light. The substance on the right in this picture did not light the light bulb at all, so it would be considered a non-electrolyte. Okay, so that could be pure H2O or sugar water, something covalent, basically. Many common cleaning products used in the home are bases, or basic, I suppose. For example, ammonia, which is NH3, is a weak base. Strong acids and bases are usually too corrosive to use daily, but can be useful in emergencies, like unclogging drains with sodium hydroxide, NaOH. Okay, and then I'm also offering some extra credit for this. 2 points extra credit because it is our last unit. Congratulations, y'all.